a formula for the first of my two megafave numbers. Note that this is all assuming that the universe is both quantized in mass and in distance. We have three variables that we need to deal with. We have r, which is equal to the radius of the universe in whatever the length quantum is, which we as a scientific community are pretty sure is the Planck mass. Not the Planck mass, we're talking about length. The Planck length, sorry. In Planck lengths. Pardon my spelling, I have no idea how to spell. I'm terrible at it. Next, V, which is going to be equal to the volume of the universe in Planck volumes. Now, a volume of a sphere, which the universe is about, is, so V is equal to 4/3 pi r cubed. That's the formula for volume of a sphere. Pretty basic. And then we have M, which is the mass of the universe in whatever the mass quantum is, which is decidedly not the Planck mass, because the Planck mass is, like, way too low. Pardon the clock. Or it's way too big. The Planck mass is way too big. It's like 21 micrograms or something, which is quite large, so it can't be the mass quantum. So the mass quanta in mass quantums. There we go. Okay, and then we also have to define this notation for choose n, choose k. This is not a fraction that I forgot to put the bar in. This is a different notation for n choose k. Say you have n objects, it's asking how many ways are there that you can take k objects out of a group of n objects. So n choose k is equal to n factorial divided by k factorial times n minus k factorial. If you don't know what factorial is, it's basically just saying take whatever number n or k or whatever the input is and multiply it by that number minus 1, that number minus 2, all the way down until you multiply it by 1. Now you don't really need to multiply it by 1, but it's just in the notation, it's convention, whatever. Okay. So then we need to define a function, f of r, where r is the radius of the universe. Again, f of r. So we're f of r gives you, given the radius, f of r spits out the number of possible combinations of the possible ways that the universe can be arranged. Actually, we're going to start with f of v. F of v is equal to the sum from m, that's the mass, equals 0, so if there's no mass in the universe. So from m equals 0 up to up to v, because we're saying that there can be either 0 mass quantums in each volume, or there will be none. There's either mass there or there's not. That's it. So the most mass that there can be is equal to the volume. So we have that. Now, using this notation again, which stands in for that, we'll simplify it down to that later. So we have so how many ways can you take out however much mass you have of the volume? That wasn't a great sentence, but you know, whatever, you can probably figure it out. So we have V choose M. Now we want this in terms of R, so we'll define another function, f of R, which is equal to the sum from m equals 0 to this equation again, 4/3 pi r cubed, and then again we need to replace v with 4/3 pi r cubed, so we have 4/3 pi r cubed, and then that's on the bottom we have m, close parentheses, so that's again in the format n choose k. Then we can simplify this more using this notation rather than this, so that we can do more things with it, because that's also hard to enter into a calculator, which we will be doing in the next video, so make sure you watch that. So we have there, I'm making this really big, f of r is equal to the sum, we're making that symbol really small, from m equals 0 to 4/3 pi r cubed. And then we are doing that with, so n, that's n, so we have 4/3 pi r cubed factorial, and then in the denominator we have again, oh bother, we have again k is m, so we have m factorial times n, which is 4/3 pi r cubed, minus k, which is m, all factorial, close parentheses. That is our equation for this.